Welcome to today's webinar, Deep Dive on Elastic File System. Our presenters today are Ed Name and David Green. Ed is the product head for Amazon Elastic File System, and David is an enterprise solutions architect here at AWS. Today with us, we also have Prash Bungale and Andy Kruge. Prash and Andy, along with our presenters, will be moderating and engaging with you in the Q&A pod, answering your questions throughout the presentation. Ed and David, welcome. Ed, the floor is now yours.
Thanks, Joe. Welcome, everyone, and thanks for joining us. I'm super excited to be doing this webinar today. We launched EFS as a generally available service about 11 months ago, and customers are using it for a wide swath of applications and workloads, which we're really happy to see. This webinar is a 200-level overview on EFS, and it's really focused on helping you understand how EFS can solve your storage needs and how to get the most out of EFS. We have lots of content planned for today's webinar, and we'll start off by talking about why and when to use Amazon EFS. We'll then talk about some key technical and security concepts. We'll dive deep on Amazon EFS's performance model and how you can get the most out of the service from a performance perspective. We'll also do a deep dive on how to load data and move data as quickly as possible, and David Green is going to walk us through some examples of doing that as part of our performance discussion. And then we're going to review EFS's total cost of ownership and its economics, and I hopefully will help you put some of the economics into perspective if you're comparing it, EFS, to other solutions. And then we will take your questions. So with that being said, we have a packed agenda, so let's get started. And I want to start with a brief overview of the overall AWS storage portfolio. And we have three core classes of storage: block storage, file storage, and object storage. So block storage, which is EBS and EC2 instance storage, is storage where data is presented to your instance as a disk volume. And block storage provides the lowest possible latency access to your data from single EC2 instances. So if you have a single instance that needs to access the data, you can use block storage to do that. And EBS is very popular, for example, for boot volumes and for databases where single access is important and you really want to get the lowest possible latencies. Skipping file for a second and going to object on the right-hand side, an object is a piece of data, like a document or an image or a video, that's stored with some metadata in a flat structure. And S3, our object storage service, provides that data to applications via APIs over the internet. So with S3, it's super simple, for example, to build a web application, delivers content to users by making API calls over the internet. Glacier also is object storage, provides an API for putting and getting data, and it's intended for archival use cases. And as of 11 months ago, with the announcement of general availability for EFS, we now have native file storage as well. And with file storage, with EFS, data is presented via a file system interface and with file system semantics to instances. And when attached to an instance, it acts just like a local file system would. And EFS provides shared access to the data to multiple EC2 instances, up to thousands of instances, all doing concurrent access to the file system with low latencies. Then at the bottom of the slide, you'll see we have a suite of cloud data migration services, and those services help customers migrate data into and out of the AWS cloud in offline, online, or streaming models. So some EFS attributes. Well, you get what you would expect from a file system with EFS. First and foremost, you get a standard file system interface and standard file system semantics. So if you are writing applications that use your operating system's APIs to work with file data, those applications will work with EFS. And EFS supports the full semantics that you would expect, like read after write consistency, the ability to take out locks on files or portions of files, etc. EFS is also shared storage. As I mentioned, you can have up to thousands of EC2 instances accessing the same set of files. You have strong consistency across all of those instances accessing the data. And EFS is highly available. Every aspect of the service is designed for high availability. And it's also highly durable. So data is stored across multiple availability zones. And so you can think of EFS as being designed like S3 in terms of durability and in terms of availability. It provides consistent low latencies, which is really important for a lot of different file-based workloads and applications. And it's highly scalable. You can create a petabyte-sized file system, and your throughput can grow to multiple gigabytes per second. The capacity is fully elastic. You don't do any provisioning of your file system. You just create a file system and it automatically grows as you add data and shrinks as you remove data, and you're billed only for the data that you're storing. And it's fully managed. So there's not a whole lot that you need to do to operate the file system and ensure that you have a highly available storage layer for your application or for your workload. And with EFS, we focused on changing the game for shared file storage. And there are three core pillars to our design for EFS. One, EFS is designed to be simple. Two, it's designed to be elastic. And three, it's designed to be scalable. And those three are on top of a foundation of high durability and high availability. And I'll quickly talk about each of these in turn. So EFS is simple. It's a fully managed service, which makes it simple to administer file systems at scale. There's no file layer or hardware to manage. There's no volumes, LUNs, RAID groups, provisioning management, none of that. There's actually really no dials or levers to pull or turn. It's designed to be super simple. And with EFS, you can create a scalable file system that can grow to petabyte scale in a matter of seconds. It provides seamless integration with existing tools and applications. It supports NFS v4.1 and also v4.0, and those are widespread open protocols. As I mentioned earlier, it provides standard file system access semantics and works with standard operating system APIs. It also provides very simple pricing. So you're charged a simple per gigabyte per month price. There's no other fees, no throughput charges, no operation charges. You just pay for the data that you're storing. Simple per gigabyte per month billing model. And EFS is elastic. File systems grow and shrink automatically as you add and remove the files. As I mentioned, there's no need to provision storage capacity or performance, and you're paying only for what you use. And EFS is highly scalable. File systems can grow to petabytes of capacity. There's no need to reprovision, adjust performance settings, or do anything in order for a file system to grow to petabyte scale. It just does it automatically as you add files. Throughput scales automatically as the file systems grow. With every gigabyte of data that you store in a file system, you're entitled to a particular amount of throughput. So you add up all of that throughput in aggregate across your file system, and that's the amount of aggregate throughput that you can use to access your data in EFS. It provides consistent low latencies regardless of file system size. Lots of file workloads are latency sensitive, and so low latencies and consistent low latencies were a super important part of our design. And EFS also provides support for thousands of concurrent NFS connections at the same time. So thousands of connections from EC2 instances. And that allows EFS to be used as a common data source in large clusters, or more broadly, really any use case where you have many nodes accessing a single source of data. And EFS is designed for high durability and availability. Your data is automatically available in multiple AZs. When you write data, it's written to multiple AZs, and you can read it from any of those AZs concurrently. And every aspect of the service is designed for high availability from the ground up, including the endpoints that you create in your VPC, which I'll talk about in a second. EFS today is available in 5 regions: US West, Oregon, US East, Northern Virginia, US East, Ohio, EU, Ireland, and Asia Pacific, Sydney. And I'm excited to share that Germany, our Frankfurt region, is coming soon. And a question I sometimes get is, should I use EBS or EFS? Because with EBS, you can format your volume with a file system. So how do you decide between EFS or EFS? Well, so some simple criteria you can use. So if you have an application and it's running either on EC2 or on premises, and I'll talk about the on-premises piece in a second, or you use a case that requires a file system and you require multi-attach or gigabytes per second of throughput or multi-AZ availability or durability, or you require automatic scaling of storage, then EFS is a solution you should think seriously about. And customers are using EFS today for a broad spectrum of workloads. Web serving and content management are really popular workloads. Database backups, analytics and large-scale clusters doing analysis on data, very popular set of workloads. A lot of media and entertainment applications and workflows, container storage, home directories, general workflow management where you want to store state information in a shared repository. All of these are very common use cases for EFS today. So let's dive a little deeper on some of the technical and security concepts that are core to EFS. And first, I'll start with a definition. What's an EFS file system? Well, a file system is the primary resource in EFS, and as you can probably guess, it's where you store files and directories, and you can create up to 120 file systems per account. And then another definition, we have this thing that we call a mount target. So to access your file system from within a VPC, you create mount targets in the VPC. And a mount target is essentially an endpoint that lives in your VPC, and it provides an IP address and a DNS name that you can use in your mount command in order to access a file system. And so the mount target is designed to be highly available because that's where you're directing all of your traffic to from your EC2 instances. So as you can see on the diagram on the right, you set up mount targets in each of the AZs from which you want to access a file system, and you use those mount targets as the endpoint for your EFS file system. So let's take a look at how you would mount to an instance with the standard Linux mount command and these mount targets that you've created. So you use the standard mount command that you would use to mount a network file system within a Linux environment. And an NFS client is required to be running, and that's standard on Linux distributions. If you look at the bottom half of the screen, we show the mount command that you would use. So the -T means you'll specify the type of mount. It's an NFS 4 mount. And the -O is for the optional parameter, which is NFS version 4.1. That's the version we highly recommend. We also support 4.0. Then you provide the file system's DNS name. So this is the DNS name that's associated with the mount target that's local in your AZ, and then the target directory that you want to mount to on your local instance. So as a summary, how does it all fit together? Well, you have a region, and within the region you have a file system. You access the file system from within a VPC, within your VPC that's in the region. You create mount targets in each of the AZs within your VPC from which you want to access the file system, and then you mount from EC2 instances in each of those AZs using either the IP address of the mount targets or the DNS name. And keep in mind that data can be accessed from any of the AZs in the region while maintaining full consistency. So you can have your EC2 instances spread across multiple AZs, all accessing the file system, and each of those instances will see a consistent view of the file system. And there are a number of security mechanisms available to your EFS file systems. So first, at the network level, you can control network traffic to and from your file systems by using VPC security groups and network ACLs. And you essentially apply those to the mount targets. So the mount targets are what are controlling the traffic that can reach your file system from your VPC. And so you apply the security groups and network ACLs to those mount targets to specify what type of traffic can reach the file system. And second, at the data access level, you control file and directory access by using standard POSIX permissions. And at the administrative level, we provide an API, and you can control who can access the API via IAM. And the API allows you to do things like create a file system, delete a file system, create mount targets, view details on the file system. So the API is really about managing the file system, and you control, again, access to that API, to those management capabilities through IAM. And as I alluded to a little earlier, you can access your EFS file system not just from within a VPC in AWS, but also from on-premises servers via an AWS Direct Connect connection. And AWS Direct Connect establishes a private network connection between your on-prem environment and AWS, bypassing the internet entirely. And one of the benefits of that is improved latencies and throughput. So with this feature, you can mount your file system from an on-prem server with the same NFS 4.1 mount command that you would use from EC2 instances. So the same command that we saw earlier, you would use if mounting over a Direct Connect connection as well. And so what does that enable you to do? Like, what are some of the things that people do when they're accessing an EFS file system from on-prem? Well, there's a couple different types of workloads. So the first is if you're doing a migration, you want to import a bunch of data from on-prem onto EFS, you would be able to mount the file system from your on-prem server and write the data to the EFS file system. Another common scenario is what we call bursting workloads, where you want to spin up a cluster of EC2 instances on the AWS cloud to do analysis of a data set, and the data set is stored on-prem. So you could use your Direct Connect mount to send your data over to EFS, have the EC2 instances work on the data on EFS, and then you can send it back to on-prem. And then the final scenario is backup and DR. So if you want to back up your data from on-prem or configure a disaster recovery environment on the cloud, you can use the Direct Connect connection to move your data back and forth. The one area that we don't recommend using EFS over Direct Connect for is tiering. And that's because let me define what I mean by tiering. Tiering is your application is running on-prem and your data would be on the cloud. The latencies over a connection that's over Direct Connect are variable, and it depends on your Direct Connect connection. But in many cases, those latencies are high enough that you wouldn't really want to run a workload where your compute is on-prem and your data is in the cloud. All right, so let's dive a bit deeper on EFS's performance and how to get the most out of it. So let me start by saying EFS is designed for a wide spectrum of performance needs. And it's really designed to serve the vast majority of file workloads. So from big data applications that are massively parallelized and require the highest possible throughput to single-threaded, latency-sensitive workloads. You can get a feel from the slide about kind of which workloads fall into which of those camps. And to support this broad spectrum of workloads, EFS offers two different performance modes. The first is what we call general purpose mode, and that's the default mode, and most customers are best served by general purpose mode. It's optimized for applications that are latency sensitive or just general purpose type of workloads, and what it provides is the lowest possible latencies for file operations. And the major trade-off for general purpose mode compared to max IO mode is you have a limit of 7,000 operations per second, which for most workloads is not a constraint. So with max IO mode, which is really designed for large scale and data heavy applications, you have really the virtually unlimited ability to scale out throughput in IOPS, so you don't have the 7,000 operations per second constraint, with the trade-off of slightly higher latencies. So if you're thinking about which to use, general purpose again is appropriate for most workloads. That's why we have it be the default. But if you're accessing from, let's say, tens or hundreds or thousands of instances, if you're accessing a set of data, chances are that the aggregate number of operations per second you're going to want to drive are above 7,000. And in that case, max IO may be the better mode for you. And what we generally recommend is that you try your application, you test your application in general purpose mode, and if it works, then great. And if you're not running into this constraint, the 7,000 constraint, then great. If you are, then you should try max IO mode. And we provide a CloudWatch metric that allows you to determine if you're actually being constrained by that limited general purpose mode. So it's called %IO limit, and it gives you a sense of how close to that limit you are percentage-wise. And to understand EFS's performance model, it's helpful to provide some color on EFS's architecture. And at its core, EFS is a distributed data storage design. And what that means is that file systems are distributed across an unconstrained number of servers. And what that does is it avoids the bottlenecks or constraints of traditional file servers and enables high levels of aggregate IOPS throughput. Data also is distributed across availability zones, and we've talked about that before as being critical to high levels of durability and availability. And so given that, how do you think about EFS performance relative to EBS performance? That's another question that we commonly get. And the distributed architecture that I just talked about has some performance implications, namely around latencies. So this distributed design results in a small latency overhead for each file operation. So if you're taking a look at per operation latency, you absolutely need to optimize for the lowest possible latencies. EFS provides low consistent latencies, but EBS, especially provisioned IOPS, provides the lowest possible latencies. They both offer consistent latencies. But if you're looking for throughput and throughput scale, EFS allows you to drive multiple gigabytes per second of throughput compared to around a single gigabyte for EBS. From an availability and durability perspective, EFS stores data redundantly across multiple AZs. EBS stores it in a single AZ. Access, you can access EFS from up to thousands of EC2 instances concurrently, and EBS is designed for a single EC2 instance in a single AZ. And what that all boils down to in terms of use cases is EFS is being heavily used for big data and analytics workloads, media processing workflows, content management, web serving, home directories, and a lot of just general purpose file storage use cases where you just want to create a file system and to take advantage of the elasticity and the high availability and high durability. EBS is a great option for boot volumes, transactional NoSQL databases, data warehousing, a lot of workloads that really the latencies are super critical. And EFS is designed to process high volumes of concurrent operations on a file system. And that means that you can send multiple operations in parallel by using multiple threads from a single instance or from multiple instances. And to show you the type of aggregate performance you get as you parallelize your workload, this graph shows on the y-axis the aggregate IOPS that EFS is delivering to a sample use workload that we ran, and the x-axis is the total number of threads. And this was across 10 M4 X large instances where we did a bunch of parallel writes. And you can see basically linear scaling as you increase the number of threads, the aggregate number of IOPS increases. So if you have the ability with your application to parallelize, you can really leverage a lot of that parallel support that EFS provides from a performance perspective. I won't go into the details on this slide, but just so you know, there's a number of CloudWatch metrics we provide that give you visibility into your file system's performance. And we have all of this documented on our website. And also very well documented on our website are our recommended kernel version and NFS mount options. Really, these things do matter. They matter a lot in terms of performance. So for example, using NFS 4.1 makes a big difference performance-wise for a lot of workloads. Really, pay attention to those things. Most of these are defaults. Actually, all of them are defaults except for the NFS version number. Really, make sure that you're using. If you are changing things, make sure you understand what you're changing and why in terms of options you're providing, and definitely refer to our documentation because these things do make a difference. With that, I'm going to turn it over to David.
Hey, thanks, Ed. So my goal here is to really move data as quickly as possible in and out of EFS. So I had two scenarios I was looking at. One was to move large media assets. So for example, some transcoding systems for media processing require support for a POSIX-based file system like EFS. So what we're doing is we're moving multiple 100 gigabyte files to EFS. and the data sources came from S3 and EBS. The other use case I was looking at was moving a ton of small files ranging in size from 64K up to 256K, again, sourced off of S3 or EBS. And before I go into the details, I want to talk about serial versus parallel operations. So in a serial operation, you basically have to wait for one operation to complete until the next one can begin. And that's not ideal for running at high performance. So what we want to do is run things in parallel. Have as many threads or processes per host running. And on top of that, we want to have several instances running as well, just to really optimize throughput and really take advantage of the performance characteristics of EFS. So here's how we did this. I use Parallel to run things in parallel, and it's online. It's very easy to use. We have some other tools as well that we're going to update online to show exactly other options of how to do it. But in my case, this is the tool I used. And I really wanted to optimize transfers. So I really wanted to show what's the best way to do it, how many threads should I be running, and how many threads I should be running, how many instances I should use, instance count. So I did testing between different instance types. I tested all the way from the small T2 up into the X. And I had 1,000 small files, and I increased thread count from 1 to 1,024. The tools I use for monitoring were Datadog for on-instance performance. I use Sumo Logic for log collection, and I use SaltStack for orchestration. And here's my results I saw with large files. I ran an initial test with 4 instances, and I saw about 451 megabytes per second access. And in the graph, we see that each instance had the same performance. So it wasn't like one was going faster than another. It was pretty well distributed. So now that we know that, let's add some more instances and see what it looks like. So I added 50 instances, all transferring multi-100 gigabyte files, and I was able to achieve 4.2 gigabytes per second on the file system on my test case here. And this is ideal for processing large media workloads. So how about small files? I really wanted to see what works best. So I ran all the instance types that we have and just really try to find a sweet spot of what instance was best and what thread count. So we see here at about 200 threads is where the performance really kind of just plateaus. So there's no really, in my opinion, on this test, there's no need to go over 200 threads. So now that we know that, I want to see which instance is really best for this. And from a cost and performance perspective, in my testing, the C3 large was pretty well, had the same performance characteristics as some of the larger instances at 200 threads. And at 200 threads, I was moving 5,300 files per minute. So now we know what I want to use, the C3 large, about 200 threads per instance. I wanted to increase the instance count just to really move as much data as possible. So I increased it to 300 instances. And to optimize for cost, I used the EC2 Spot market, which allows you to bid on excess capacity. So to do that, in the Amazon console, when you launch instances, I select 300 instances up on top there. And then I select Spot instances. And during my testing, the Spot pricing was 1.6 cents per instance hour. So it's very inexpensive here to be able to do this. So with the final result with testing, I was able to move 1.6 million files per minute. And the graph below, it's kind of condensed, but it really shows a lot of, it's just really evenly distributed across all the instances for performance. So side by side, I was able to move, a lot of data on small files and a lot of throughput on large files. So in summary, please parallelize everything. This is true for not just EFS, but overall operations on AWS. It's really best to decouple and parallelize as much as you can. And please test the performance numbers I show over for my application and my test, but every environment's unique. So please test on your data set and tweak some things around, and things might work differently in your environment. And I like to always capture and analyze, because that way you have data-driven results that you can show with hard evidence. Like, this is the result that I saw, and this is how I can replicate this test. And in the testing that I did with the spot price where it was, I ran this test for $5 an hour for 300 machines, 300 EC2 instances. It's really nice to be able to leverage the scale and cost efficiency of AWS. So thank you very much.
All right, thanks, David. And speaking of economics, let's talk briefly about EFS's economics. So as I mentioned earlier, with EFS, you pay only for the storage space you're using, and there are no other fees. In our US regions, you pay 30 cents per gigabyte per month, and other regions we have slightly different global pricing. You should check our website to see what our prices are per region. But how do you put this 30 cents per gigabyte into context? Well, one way to do that is to understand what it would cost to build your own shared storage solution on top of AWS using some third-party shared file layer. And so the typical setup for something like that, which I'm showing on this screen, you would have a NFS client that's accessing your file system, so similar to with EFS. You will have an EC2 instance that you would set up in each AZ. So most customers look for a multi-AZ setup for availability reasons and for durability reasons. So you would have an EC2 instance that's managing the file layer, and then you would have EBS volumes attached to those EC2 instances. And so you would duplicate that across each AZ for which you want to replicate your data and have it available. And so as you can see in the diagram here, you would have two EC2 instances if you wanted in two AZs, and then two sets of EBS volumes to store the data, and you pay for inter-AZ traffic between those AZs for actually replicating the data. So what would this come out to in terms of total cost? Well, let's say that you need to store around 500 gigabytes and you require high availability and high durability. So you want to have your data stored in at least two AZs. So using a shared file layer like we talked about on top of EBS, you'd probably provision at least 600 gigabyte EBS volumes, and you would fully replicate the data to a second AZ. And so just the storage, the EBS storage, would be $120 per month. So you're paying for 600 gigabytes times 2. Your compute costs, 2 M4 X large instances would come to $350 per month, and this is for the EC2 instance that's managing the storage layer in each AZ. And then you have your inter-AZ traffic at a pretty reasonable, actually fairly low level of replication, so fairly low level of writes to your file system. That would add up to about $130 per month. So the total cost that you're looking at is something like $600 per month. With EFS, your cost would be 500 gigabytes times 30 cents, $150 a month. So that's it for the content on the webinar. I'm going to turn it back